So we're going to talk today about virtual memory and paging, really, and virtual memory as a use of paging. This will be the first of 2 lectures. So Wednesday we'll talk in more detail. Really what we're going to talk about on Wednesday is more applications of virtual memory, so different things that you can do. So let's look at this kind of from the most simplest case. So hold on just a second. All right. So in order to do multiprogramming, we have to have multiple processes, right? If we're just doing single uniprogramming, a single task running on a machine, then it's pretty straightforward. It uses all the memory, right? So one possibility for how we could do multiprogramming is we could have one process in memory, so an OS kind of sitting at one part of the memory, and a single process taking the rest of it. In order to have another process run, we've got to have that process in memory, right? So we would actually have to yank this process out, put in the other process, start it running as well. Kind of expensive. I mean, if this ran to completion, then it's really just a batch system, right? Where we run one job, and then we run another job, and then we run another job. I'm talking about actually going back and forth. So if we're going to go back and forth, we've got different parts of this process, right? We've got some code, and we've got some, I'm going to call it dynamic data. We might also have some static data, pre-computed read-only arrays, things like that. If we throw process 1 out and want to bring it back in, where can we get this code and static data from? Okay. The executable, right? Where we originally read it from the executable file, the a.out. But the dynamic data we can't, right? The dynamic data was calculated dynamically by the code. So that means before we kick process 1 out, we would need to save its dynamic data. Okay? To where are we going to put it? I guess disk, right? So, and then we could bring in process 2, bring in its code, bring in its dynamic data, and have it run. This is extremely slow because dealing with the physical disk is just much, much, much slower than dealing with memory. But that's one thing you can do. Okay. Another possibility then is go ahead and put multiple processes in memory. And we'll do something simple to start with. We'll do fixed size partitions. So n is going to be the size of our partition, and every program is going to get n space for its code and its data and so on. And n has to be as big as the largest program that will run. Or another way to put it is if n is bigger than a particular program you want to run, you can't run it. Right? So that'll work. And then if the operating system wants to switch between running different processes, it doesn't have to worry about the memory because it's all there. It can just suspend executing one process and go into the stack and the instruction pointer into a different process. This does lead to some wasted space. If we make sure that kind of the size of our OS plus these n's fits all of memory, we don't have any wasted space there. But we do have wasted space within each block. All right, so assuming, I don't know, let's say this process doesn't use this amount of memory. And process 4 maybe is a smaller process. And process 3 is echo, right? So echo uses hardly any. I'm marking the stuff that's not used, which is maybe not the right way. But so echo is small, and this one is, let's say, GCC, and that's big. This space is called internal fragmentation. So internal fragmentation is unutilized memory within a block, within an allocated block. And it makes sense. There's going to be some if we have fixed size partitions because programs need a different amount of space. So we're going to just kind of work our way up. Well, what if we have non-equal partitions? So same deal, they'll be fixed size. When we start a program, we'll give it a fixed size partition, and that's how big it'll run in. And that works. We no longer have the internal fragmentation issue, assuming that this size was correctly specified. This is how the Mac used to work pre-OS 10. You could actually specify how much memory, how big a partition the application would get. And so we have different sized ones, which is great. But we can have fragmented memory between allocated memory blocks. Let me show you an example. So let's say process 1 finishes. Okay? And then we've got 4 starts. So let's say, so process 1 isn't there anymore. And now we have process 4 in this area, because it doesn't need very much. And then let's say 3 finishes. And then, so process 1 finishes, process 4 starts, process 3 finishes, and then process 5 wants to start. Here's the problem. Process 5's memory needs are 1 byte larger than this hole right here. Okay? Is there 1 byte available, Drew?
So if you finish 1.
We did finish 1.
Right.
And we started up 4 in just the top area of 1.
Okay,
so this part's free.
Right, so there is space, but it's not contiguous. You can't allocate it.
That is exactly the problem. There is space. It's not contiguous. That's really a good description of all of fragmentation. There's space available, but it's not next to each other available to be used. Okay? So process 5 wants to start, needs a block bigger than this. So the memory exists, but it's not contiguous. Okay? And here we've got external fragmentation because the memory that's available is between allocated blocks. Right? It's sort of the memory allocators has the memory, and if there were some way to put them together so that we're contiguous, this could all work. Does that make sense? Any questions? All right. So let's go back a second. We had this idea that we could actually load different processes in memory at different locations. How exactly is that working? Let's just look at that, because it's not necessarily clear that that will work. In fact, let's see, if we look at the kernel, right, for XV6, we're loading it at a particular location in memory and expects to be running at that from that location. That's where it's going to be loaded. So one question is, when do you map instructions, that is things like jumps, where you have some address here, and data references to specifying some actual memory location? So we could do absolute addressing, link time. So an example here is the XV6 kernel, or the JOS kernel, same thing. Okay? And in general, ELF format, as we saw, has an entry address of where you start executing, and that is the address where it expects to be loaded and run from. There are other options. Okay? You could have code that can be loaded anywhere in memory. So one thing you can do is you can have a linker loader that actually modifies code as it's being loaded into memory. So what we would have here, we can have a jump address here, but in our executable. So our executable would have code, and then it would also have I'm going to call it a fix-up table. okay? That's going to have the address of every one of those. So every target of a jump, it's going to have. I mean, you can imagine a slow link loader that just goes through the entire code, disassembles it, finds any jumps, knows how the thing was originally linked, right? Assuming it was going to be loaded at location X in memory. It's now being loaded into location Y, so it updates every one of these addresses and adds Y minus X, whatever the appropriate manipulation is. We can make it quicker by having this fix-up table. So we know where every jump is, okay, every jump instruction, and it'll go fix every jump instruction. Does that make sense?
But don't you have things other than jumps as well? Like you could just have a pointer variable that is pointing to one of your global variables?
I'm just dealing with instructions. Okay. We still have to deal with data references too, and we could do basically the same thing. So we could also have a fix-up table with the address of every global reference.
Well, things like function pointers.
So yes, so let's say function pointers would be another one we have to deal with, right? Because a function pointer, we're loading the address of a particular instruction in memory. But it's a doable problem, okay? But a little bit slow. Easier if we can get the compiler's help to not generate absolute addresses in the first place. So one thing you can do is you can have position-independent code, for example. So position-independent code, you're not going to jump to a specific address. You're going to instead, when you do a jump, let's say 500 plus 500 from the program counter, or minus 500 from the program counter, or something like that. So it's just going to be relative to where you are, and that then is position independent, right? Doesn't matter where you're loaded, as long as the code you want to go to stays 500 from where you are, it works.
What if you need to jump further than, like, I'm sure there's some maximum distance around the program counter that can actually be specified.
You can always do it. So on the Mac, and I was a Mac programmer, so this is why I know all this stuff. The PC relative used it used a 16-bit value. Okay, so it could be 16-bit, 16 forward, or 16 back. So what that meant is, as long as your code wasn't any larger than 32K, you could get anywhere you needed to get, right? You could create larger ones. You just had to make sure that no jump ever went more than 16K, which meant sometimes you had to put in little helper functions. You know, if I want to get from A to X, I might have to go from A to a new routine J that all it does is turn around and call to X. Okay, craziness, right? And then you can actually get around that because the compiler can always generate code to do 32-bit or 64-bit manipulation of the program counter, right? It can read the program counter, do some manipulation, then do an indirect jump through that. So it's possible. So.
Is there any reason why you wouldn't want to use position-independent code over like these other?
And it's MAT, right?
Yeah.
Any reason you wouldn't want to use position-independent code? There might be a speed penalty. Certainly in the case I was just talking about, where you might have to actually do some calculations and stuff, you know, because the compiler doesn't actually support it. There is, so ELF won't work with, is not a suitable container for position-independent code. There is, I think it's Pi or Pix, position-independent executable or position-independent, yeah, executable. They're just not clear whether the executable is an E or an X, so it's Pi or Pix. Their subroutine calls RPC relative, and it's an alternative to alpha format. And you still got to deal with data references. Again, going back to the Mac, just because it was such a simple way to do it, every global variable you'd never reference directly. You always referenced it via the A5 register. Okay, so you would always go via A5, and then from there, there'd be your blob of global variables. You can see how that would work, and then if you want to switch processes, you just change the value of A5. You could do something similar, basically, so that your references to global variables don't use an absolute address. They indirect through some pointer that points to them. And then all you have to do is update that pointer. Make sense? Okay, so that's how we're actually getting. I never do understand why that happens. Like, ink, go away. Anyway, that's how we're getting these different processes to run separately. Now, it'd be nice if we could not have to worry about it. If our code could actually be position dependent, and yet it's not executing from where it thinks it is. So the idea is, wait till execution time and have the hardware help you out. I'm going to assume that that stuff will just go away eventually. So for a process, the process is going to see an address space that goes from 0 to n. And we're going to have a relocation register that gets added to every address reference, whether it be instruction or data. So that gets added in. And so for process 1, it's going to be from A to A plus n because we set the relocation register to A. If we look, for instance, at a process down here, we would set its relocation register to A plus 2n. Okay? But the actual code that's generated just thinks it's operating from 0 to n. Gavin, any problems with this?
What if you try to access what if your process tries to access something that's after?
Yeah, I try to access down here.
Say n plus 7.
Okay, and that's really down, trying to keep that about the same distance. Here, is the hardware stopping me? No. So what we can add in is some protection. Okay, now we have, great, more access. Well, we'll just have to live with that. I'm hoping that it's going to sync or something. No, I don't. Well, tell me what you don't like. What can be better? As a matter of fact, I have some ideas.
Have you tried erasing it?
Why don't I do that? That's a good idea. So let's see. Yeah, I don't think it's there. Whoa, but if I went up and erased it, where?
Oh, and it's bad. It's fixed itself.
Okay, nice. Thanks, Nandika. Okay. So the idea is, as well as have a relocation register, also have a limit register, where the limit register says how large is your address space. So when we try and use an address, first the hardware says, is it less than the limit register? If so, okay. If not, that's an exception. And then we add the. So that way, these guys can only see within their area. Right? There's no way to get outside.
How does this solve the external fragmentation problem?
This solves the, in this case, this addresses neither the external or internal fragmentation problem exactly. What it would allow us to do, so let's talk about the, do I have it here? Yeah, we'll get to that in just a moment. So it's a good, there, see, I can look at them line up right there. We don't need that anymore. So I'm going to erase that, and then I'm going to hope it goes away. No, the one of them goes away. Fabulous. One thing about this, though, we can't easily share memory between processes. So, not going to work. So we want to protect the memory of a process from other running processes. The way we just talked about will work. That's great. We can, as I mentioned last week, use a system where we don't have any raw pointers. So something like Smalltalk or Lisp or something like that, where we've got tag data that limits our ability to just go at memory addresses. Within our address space, this is commonly what things look like. We have our text or code segment. Why it's called text, I don't know. It's kind of historical, but code and text are equivalent. We've got our data, which is our global data, which is, Jonathan, is this fixed size, our global data? Or does it vary over time within a particular process?
That data over there.
The data right here.
I'm going to go to fixed.
And you're certain of fixed, clearly. So yeah, fixed is right in the sense that when you compile and link your application, it sets up some global, and that's all there is. Okay, as big as it is. It's a question about.
The acronym BSS, does that go with the global variables? Or?
Yeah, this is BSS, which I know what text means. BSS I never remember. I think I've known once what BSS stands for. What's that?
Like blank stack space or blank segment space, something like that?
Maybe. So BSS, there is a distinction here in your data between data that is initialized to 0 and data that is not initialized to 0.
Yeah, that's kind of
Okay. And I think the BSS is the one that's initialized to 0. I'd have to look that up. So a lot of times that's the initial value of things. And so it is much easier to specify, I would like to have this area, 4K, and it all be zeros, than it is to say, I want to have an area that's 4K, and here's what I want to fill it in with. It's a static array in C, and I've got, I don't know, a 1 and a 5 and a 3 and a 2 and all sorts of things here. Because I have to actually provide all this in my executable, and I have to go through and either copy it over or initialize it, or somehow I've got to run some code to do this, as opposed to just set it to 0, or more likely, ask my memory allocator to give me back a page that is 0. Okay? In fact, we'll even see some other tricks as to why it's nice to on Wednesday. So in C, Aaron, okay. In C, what is the initial value of a variable? That is half right. So what kind of variables are initialized to 0 in C? Nope. Not all ints, not all pointers. It doesn't depend on the type. It depends on its extent, that is its lifetime. So we have two different lifetimes in C. We have static, and we have I don't know what we call it. Let's see what the other name of it is. Dynamic, stack-based. Okay, if it's on the stack, it has a value and then it goes away. So if it's on the stack, you have no guarantee as to what the initial value is. But if it is static, that is, it is in this data segment, you're guaranteed it'll be 0 unless you specify some alternate initializer. And the reason for that is because we got this nice, easy way to initialize to zeros. There's no nice and easy way to do that for the stack. Right? When you enter a function, whatever's on the stack for the local variables is garbage, and you have to explicitly go and set it to 0. This was kind of almost free, and so therefore, that's why C has this different rule, which, of course, is confusing to people. I thought these got initialized to 0. Well, yeah. If you put the word static in front of a variable that is in a function, right? Its scope is local, but its extent is this global, and so it gets initialized 0 too. We got the heap and the stack, and commonly the stack grows down, right? On x86 it does. And so normally we have these two things that are growing, and we'll put them at opposite ends of the rest of our address space. So this at one far end, this at another far end, and then both of them can start allocating, right? The heap, that's where we get stuff like malloc. Right? Anything that's malloc or new comes from the heap. Anytime you're dealing with allocating memory and deallocating memory, you also have these fragmentation issues. So malloc a memory allocator has to deal with both external and internal fragmentation as well. Questions? Okay, so let's go back to this external fragmentation. We have this, let me go back. Where's this? Lovely. Okay. What you can do for external fragmentation, you can compact. That is, move blocks around to make space contiguous. This only works if the relocation, I suppose you could actually execute code to go update. So move an executable somewhere else. You can't, because you might have internal pointers in your data, right? So if you have an internal pointer from one location in your dynamic memory to another location in dynamic memory, it is unclear how a linker software could move it somewhere else, know that it was a pointer, and update it. But if you're using the relocation register, the base register, just change the base register, right? Actually move it in memory, change the base register, and your process will still work. So, let's see, was this your question, Brad? Was it your question about, can this help with, how does this help with external fragmentation? Okay, it was yours. Okay, so that's how it can help. But it's still expensive because you've got to actually move the stuff in memory. You've got to move that entire n bytes. Compaction, by the way, was how Windows and Mac used to work, all in software. You didn't ever store, you almost rarely stored pointers. You all instead stored pointers to pointers, which were called handles. So this is a pointer to a pointer. And the block of memory you allocated here could move, and then they would just go update this address. The memory manager would go update that address. And so that's great, except you have to know when memory might move and when memory might move, and you have to lock it before you use it sometimes, and then unlock it afterwards, and it turned out to be a mess, but in those very small memory devices, it was necessary to sort of eke out every byte. So one possibility is compaction. Another possibility is don't require all of the memory of your process to be contiguous. And that's where we get into segmentation and actually paging as well, both of which we'll talk about today. For internal fragmentation, there's not a lot of solutions except don't use fixed size blocks. And that's all I really have for you there. Your trick is not working, Nandika.
You could try turning it off and on again.
Actually, I could quit OneNote and come back in. I like that. Is that a ta-da? All right, so I just need to quit and come back in every time I switch pages. All right, so segmentation says we already have separate address spaces, right, between processes using this base and limit register. Segmentation gives us multiple address spaces within a process. So that's kind of handy to separate out, for example, the stack into its address space from the heap with its own address space, because now we don't have to worry about them colliding.
Sorry, the address space just because it's referring to the physical address space. Like now you're saying that all of these logical paths are kind of contiguous in physical.
So stack is already contiguous. However, I'll give you an example. And actually, this is internal. So now that I think about it, this is a good example of internal fragmentation here. This can lead to internal fragmentation. Because what if I'm not using all that much, right? I've got a small stack, I'm not very recursive, and I haven't allocated much memory. But I've still got a lot of space used here. So this is internal fragmentation that could be used somewhere else. By breaking it apart and saying, okay, I'm going to have my heap this big and my stack this big, that frees up this space here. So we don't just say you get one giant address space. We say you're going to have smaller address spaces for each component of your program. Ooh, did you see that? It just scrolled right up. Oh, but this is black. Maybe it's because I was doing green.
Well, the red was also.
Yeah, that's true. Okay, so we convert this process with a single segment into a process with multiple segments. Our text, our data, our heap, our stack. The nice thing about this too is that we can specify protection easily. So we can say, this segment, let's make this one be read-only, right? So that we don't allow self-modifying code. And actually, let's make this the only one that's executable. Okay, so to prevent buffer overflow, some buffer overflow exploits. We'll have our heap. That'll be read-write, but not execute. Our data, read-write, not execute. Our stack, read-write, not execute. Okay? Maybe we'll make our heap execute if we are dynamically generating code. Right? We're doing some virtual machine we're writing, let's say. We're doing dynamic compilation. Dave?
Why couldn't you do this before? Like, specify.
Where is the problem would we do that? So right now what we've got is, sorry, where did our base register go? Right here. We've got our relocation register and our limit register. We would need to get processor support for this in order to be able to say, if I am retrieving an instruction, let's see, am I allowed to retrieve an instruction from here is really what it is, more like. And so we'd have to somehow block out different parts of our process in order to be able to do that, which would end up very similar to what we're talking about, which is 7 segments. So how does this work? All we really need is a base and limit register for each one of our segments that we support. Okay? And if we want to have protection, we'll add another register with some information about protection. The only problem is, and we could share code and or data between processes fairly easily, because you can imagine saying, let's go ahead and share this segment with another process. The problem is the programmer or the compiler, somehow we have to be aware of these different segments. Right? We're going to, let's see, I have an example in just a second. So it's easy to share segments between processes. We get this protection. We get rid of that internal fragmentation where we've got our large address space and we're not using all of it. Here, we have more granular sizes that we're specifying. We're still needing to specify our maximum stack size and our maximum heap size. And we still have to worry about external fragmentation because every segment has to be in contiguous physical memory. And then we have to be aware of it.
Sounds like we need more registers. The way you might have registers would be a lot.
So we're going to have a segment and a base limit register. So segment register and a base register. And let's say we're going to support on our architecture 4 segments. Okay? So we'll have segment register 1, 2, 3, and 4. Base register 1, 2, 3, and 4. And then we have our other registers too, our stack pointer and our instruction pointer and so on. When we swap processes, we'll save these and swap them. Yep. Does that explain that? Yeah. Okay. Sure.
Base registers refer to where each of these segments start.
Base register is where it starts, and the limit is how it is the size of that segment.
And the segment is the offset into them. The segment registers, are they like offsets into each of these segments?
The segment register, sorry, what did I mean here? What I really mean is we have 4 limit registers and 4 base registers. And a combination of a limited to base is a segment. Other questions? Yeah, thanks for correcting that. All right, so x86. Guess how many? 4 segments. Code segment, stack segment, data segment, and the extra segment. Okay? And a segment register doesn't directly contain the offset and the base, but the base and the limit directly. It indirectly describes that. So we have got in the segment register, whether we're using a local or a global descriptor table, so globals can be shared among all processes and locals are specific to that. We don't care about that too much. The requested privilege level is interesting. So that goes back into the current privilege level, which can be 0 or 3. That's what we use. And so you can specify a privilege level. That is, you have to be at this privilege or below in order to execute or to use this segment. So if I want a kernel segment that can't be utilized by the user, I'll just set this RPL to 0. And then when someone tries to use that segment register and access something in that segment, they'll get a privilege violation. Make sense? Okay. And then an offset into a descriptor table. And the descriptor table basically, so roughly what happens is our register refers to a table. And within the table, we have a particular entry. And in the entry, we have base, limit, this DPL, and whether it's present or not. Okay? Because you can have entries in here that just aren't used. So we're going to have a different entry for our code segment, our stack segment, and our data segment. Right? There'll be 3 separate ones. And the exact, so let's see, our 32-bit segment, our base register is 32 bits. Our limit register is only 20 bits. So this affects the granularity of the size that you can generate. Because you can actually, there's a setting you can set as to how big each one of these 20-bit entries represents. And it can be as large as 2 to the 12th. So you can effectively address a large range. You just have a lack of some granularity, which means you're going to have some external or internal fragmentation. Let's say you want a stack that is 3.5K big, but the minimum size you can specify is 4K big. So let's see. Who's next? Radon.
That should be external fragmentation.
So we asked for, in some sense, or want, 3.5K, and we got 4K. So that's internal fragmentation, exactly. Indika.
Is the data segment the global variables, or is it the heap?
Data segment is would be global variables, and I think the heap as well would normally be, yes, the heap as well. So let's look at how this works, and then we'll look at an example. So an address, a logical address, is not just a 32-bit value. We also have some selector specifying what segment this is. Okay. We use the selector to go to a descriptor to get a base address to add to the offset. And that gives a linear address, and we're going to later on talk about paging, which comes after this. So we just add the offset, like we looked at before. The question is, so let's look at a simple example. We got a code segment with 40, it's very small, 40 bytes, a 32-byte heap, a 12-byte data segment, and a 35-byte stack. So the heap, we could use the extra segment for that, or we could use the data segment. And let's say this is the code we have, okay, starting from location 4. Oh, and in memory, The code, the data, the heap, and the stack are all contiguous in that order. And our bounds and limit are as we see in this table. They're all present. The DPL is 3, so we're allowed to run as user mode. And these limits should match what I have over there. And our registers, so the code segment contains offset 1. That is here. And 2, and 3, and 4. So we're going to go execute this first instruction. What's the first thing the CPU has to do, David, to execute that first instruction? Here. The move instruction, yep. Say that again? Okay, so it's going to move the instruction pointer from 2 to 4. I did it. I'm the processor. I did that. Now what? Wait, look at the stack for? Well, there's two things. One, this is an indirect reference, right? So this is moving whatever EBX points to into EAX, right? So we don't have any use of the stack. But before we know it's a move instruction, how do you know it's a move instruction? All you told me to do was increment the instruction pointer, so it's 4 now. Yeah, you have to, well, before even interpreting, you have to fetch it, right? So we have to fetch the instruction from memory, right? So we fetch it from memory. What's the offset we're going to use? Sarah.
It would be the one for text, so 34.
Well, let me back up a second. We're fetching the instruction, right?
Yeah.
From what location in memory are we trying to fetch the instruction?
4.
From 4. Okay, so the offset is equal 4. Does that make sense? Right, the offset is 4 because that's where the instruction starts, right? Our instruction pointer is now 4. So we go get the instruction at 4. So it goes out to memory. It wants to go out to memory. We know it's at 4, but it's at 4 within what segment? Code segment. How does the processor know that it should be using the code segment for this memory access rather than some other segment? Pascal. Well, it's going to use the segment registers in order to determine which of these segments it is. But how does it know which of them to use? How does it know that it should use CS and not DS or SS or ES? Yeah, but it makes sense to be using the code segment. How does the processor know when I am trying to fetch an instruction, it should use the code segment?
Oh, I have a question. What does CPL mean?
It's the current protection level. Why do we have it in here? Yeah.
Does it belong here?
Say that again?
Does that information belong in the segment register?
I am trying to remember this one. And why is that here? And I'll have to get back to you. So why?
It also says that there's supposed to have like a global descriptor table bit.
There is. There's more in here. Global descriptor table versus local descriptor table. So there is a little more in here that I'm not showing.
Okay.
Yeah.
And the answer to your questions is that it uses like a different bus, right?
There's no different bus for instructions. Instead, here's what it is. If I'm fetching an instruction, guess what it is? Instructions are code. So the hardware says if I'm using EIP, I'm going to say it's code segment. Okay? Now we move EBX. So that means we have to get the EBX register, which is, we don't see what the value of it is, but it's something. Oh, I'm sorry. So we use the code segment, so it's going to use the code segment register. It's going to use the offset. It's going to go down to here. It's going to say the bounds is 104. So it's going to be 104 plus 4 is 108. So we're going to fetch the instruction from physical address 108. Why 108? How does 108 work? That doesn't work. The code is at 34. So how about 38? Does that look better? And I'll even write it out. 34 plus 4 equals 38. And I see what I'm doing. How do these pictures not match? Let's see. Hold on a second. Our code segment is 40 big. So this says 40, and this says 34. So this should be 34, right?
Well, it seems like you just have to look at the descriptor table in the right order, or the offsets in the right.
It seems like the bounds.
Oh, 34, 38.
Yeah, it's that one.
Like your limit is right, but your bounds.
Okay. Let's try this. I think they're wrong. I think they're the wrong order. I think this is 34 plus 40. And then the next one is the data segment from 0 to 12. And so that's going to be 74. I agree with you there. And then this is going to be 86. And this is going to be
I feel like an easier way to fix this is just in the registers change the offset equals 1 into an offset equals 4, and the offset equals 2 into offset equals 3.
Is it- the limits aren't correct. No. Okay. I really apologize for this. Here's what we have. We have all right, here's what we have. I'm going to just declare that's 34. Okay, so that one is 34. So the offset's going to be 34 plus 4 equals 38. And then we're going to declare what the rest of these are over time. And my limits may be wrong, and I'm sorry about it. In fact, let's just use this as our values we're going to use. Okay, 34, 72, 104, 144, and let's assume that the limits are fixed appropriately. So now we want to get the EBX register. To get the value of the EBX register, we just get it, right, as a CPU. And now we need to indirect through that EBX register. Gary, where are you? Okay. Yeah, so here's the question. We've got the value of EBX. EBX is 6. Okay? So we want to now indirect through the value 6. That is, use the offset of 6 to get the value here from our data segment. How does the processor know to use the data segment? Or does the processor know to use the data segment?
Yes.
It does. In fact, you're right.
Would it be like the same way in you how to use the code segment?
Kind of. It is the same way. In fact, let's skip that one for a second. If I did a push of a value, what segment would it use? Stack segment. Because it knows pushes deal with the stack. So anytime you are either indirectly by using push or pop, or directly by manipulating the ESP register, it's going to use the stack segment. Okay? And any of the other ones, except some very small, weird instructions that we don't care about, use the data segment. And if you want to use the extra segment, you have to specify that explicitly. And in any instruction, you can put a prefix that says, use this other segment instead. Dhruv.
All of these rules for knowing where to go in with segment, where is it specified?
In the architecture manual for the processor.
So it's like
It's all in hardware. Yep.
But, so what if EBX has a pointer
Right on.
to something that's on the stack? Then wouldn't you want to look it up using a stack segment instead of a data segment?
Well, then you'll need a stack segment prefix.
So let me back up a second. That's a problem for programming. So in programming, you would actually keep track of a pointer to something that's on the stack versus a pointer that's not, which is why we hate using segments.
Oh, okay.
So,
So we can consider
yeah, so the question was, let's say we have a pointer, and it's a great question. So let's say we got our data segment, and we've got a variable here whose value is a pointer, and it points, I don't know, to here, okay? Then we should use the data segment to indirect the pointer. But we could also have a pointer, just as easily, that points to something on the stack, right? In C, we can easily, take the address of something on the stack and save that value, as long as we don't return from that routine. I remember that beginning C programming problem. So basically, we have a pointer to a different segment, and then we should be using the stack segment for that. And the answer is, when you're programming in C in a situation like this, you have to actually have different declarations for pointers to things on the stack versus pointers to things that are not on the stack. Or, here's what it actually is. You would actually say far char star S. And far says, this isn't just one of these simple old offset pointers. This is actually glom on the segment and the pointer and the offset together. Okay? So you don't really store it as this is a pointer to something on the stack. This is a pointer to something that could be anywhere, and therefore, to store it, you don't need just the 4 bytes you normally need. You'll need whatever it is, 6 or 8, to have not only the offset, but also the segment. And by carrying around the segment and the offset, you have everything to get to it. Okay? But that all then causes your pointers to be larger, and it's a mess. Questions? Yes, but we have a solution. Oh, that solution works, but let's do the other solution. I like that one better. Look at that. Okay. So the takeaway then for segmentation is a couple things. One, the processor has some ideas of what segments to use for what different things as it's executing. Instruction pointer, stack pointer, other is the most common. And second, sometimes pointers can get pretty complicated if you do it this way. So another way we can deal with this issue of fragmentation is with paging. So the idea here is you have, again, a virtual address space, which we had with segmentation too. Okay? So in segmentation, our virtual address space just changes by translation, right? By adding a value. Here what we say is we're going to treat individual subsections of your address space differently. So we're going to say our address space looks like this. So we have pages of size k. So the A, the B, the C, and the D page. And they're stored non-contiguously in physical memory. These are often called frames, the same size chunks in physical memory, or sometimes we talk about virtual pages and physical pages. So if you hear the word page, you can't quite know we're talking about the virtual, but if you hear the word frame, you know we're talking about the physical.
So what is the advantage to using this as opposed to segmentation, just less fragmentation?
We deal with a few things that we'll get at in just a moment. Okay? And it's not an either-or for segmentation and paging. Right? In the x86, you have both segmentation and paging available to you, and they will operate together. The fact is, in most kernels, though, we just don't even use the segmentation. external fragmentation can be solved here fairly easily, right? Because as long as we want things in 4K chunks, we can use any of these. These might as well be contiguous, because I can easily create an address space where these unused chunks are contiguous, right? Because I need to just set up a mapping such that we go, let's say, here first, here second, here third, here fourth.
If we have pages, then why do we need segmentation?
The short answer is, if you have paging, you don't really need segmentation. So why does the x86 have segmentation and paging? Because segmentation was there first. But you certainly, many processors do not have segmentation. But I would say at this point in x86, it's mostly legacy.
Okay. Is
So.
segmentation usually turned off?
There is no way to turn off segmentation. So we can set the base registers to be 0, and that's what we do. Yeah.
And that's what happens on the labs too, right?
That's right. So that's why we don't really need to worry about segmentation too much, because we just set in 0.
Do you know any programs that like people still run today that use segmentation?
I guess if you go run Railroad Tycoon in a DOS box, it's probably using segmentation. But nothing. I'm sure there probably are some, but I don't know. All right. So how do you implement this paging? Right. The way you implement it is you have to have some sort of a table that provides this mapping. And this is part of the reason this is part of the expense of paging, is we need a page table. So here's our address space. Here's our page table. So our page table is going to say the first page is located at frame number 3. And it's readable and executable. And then the next page, location, readable, executable. The next page is not our code anymore, so we're not going to make it executable. We're just going to make it read-write for our data in our heap. We have a bunch of invalid, and then we have one that's read-writable at the bottom. So how big is our stack? So currently, Ryan. There you are. The question is, for this particular process, with this particular page table, how big is the stack? Or how big can the stack get?
Can it just keep growing?
Not without changing the page table. So assuming we're not going to change the page table, how big can the stack get? So our stack is starting here at the bottom of our address space, right? And here's the bottom of our address space for our page table. So we can see there's one page allocated. And then above that is invalid. So our stack can only be one page big. Because if we started using into here, it'd be invalid. And the hardwares are going to say, you got a what? What sort of an error do you get, Brad? Do you know? I don't know that you are supposed to know, but I'm just curious whether you know.
Not sure.
You get a page fault. So that's a particular kind of exception, which is something went wrong in the paging. And it is true, you could go fix it up later. We'll talk about that on Wednesday. So the part of the address space that is unallocated, we don't allocate any physical memory for it, which is nice. So we're not, the previous case where we were using just base registers, anything in between here still was using physical memory. Right? We still had physical memory allocated for it in this one giant contiguous in-sized physical memory. Here, we're not. Okay, so that saves us some space. And again, just to look at this, let's say, so this is 3, says that the first part of the code, starting at logical address 0 or virtual address 0, is at frame number 3. we don't provide a full physical address here. Giselle, why don't we provide a full physical address? Or why don't we need a full physical address of where this page starts in physical memory? And I'll give you, well, let me ask you this. Can we start any of these frames in physical memory anywhere we want in memory? Or do they need to be some sort of alignment?
So they're definitely on like a nice boundary.
Yes. They're going to be on the same boundaries as this is going to be. And so therefore, if these are 4K pages, these are going to be 4K frames. And so therefore, all we really need to know is the frame number, where the frame number is going to be identical to the address right-shifted divided by the page size. So 0, 1, 2, 3 gives us the first one of our 2 pages for code. 1 gives us the second one. 0, 1, 2, 3, 4, 5 gives us our 1 data segment. 1 data segment. And then 8 and 10 happen to be our heap. And then we got a stack here. So all this part, didn't have to allocate memory for.
So
Dave?
Two questions. So the thing in the thing in the middle is like our page table.
Yeah, so this one is our page table.
And so that
This is our physical address space. And this is our virtual address space.
So your page table and virtual address space are like ordered in the same way.
Yeah,
Okay.
have to be.
Okay.
Yep.
And so then how does it know here the difference between like data and heap?
It has no idea of difference between data and heap. All that happens with the processor is if someone is dealing with the heap, there's a particular address. And it will take the address, strip off the last so many bits, use that as an index into here, find what page it is, look and see what permissions there are, and whether we're trying to write into read-only memory or execute non-executable. And then assuming it does work, use this value, take the bits we stripped off, and slop them back on into here. So it basically gives us an offset into the actual physical address. Aaron.
So there's a diagram of like logical address to linear address here. If the segments are, the base is 0, then the offsets basically become the linear address, right?
So that's the combination of paging and segmentation?
Just segmentation.
Is that?
Oh no, it's cycle 4.
Oh, this one here.
Yeah.
This one?
Yeah, yes.
Yeah. So I just want you to, now as we're getting into paging, so this happens to provide us an address that then we go send to the MMU, use the page table.
But since like usually on modern devices, the base segments are 0, so the offset is
That is,
the offset is
yeah,
the linear.
the offset is the linear address, yes.
Okay.
If this value, this base address is 0, then the offset is a linear address, and that's how we set things up. All right. So how does this work? It's done in hardware with the memory management unit. We have a page table register that points to the beginning of the page table. And there has to be somewhere that specifies how big the page table is. Because if you only need a little address space, right? If you're a process and you only need, I don't know, 0 to 1 meg of address space, then maybe there's no need to have an entry for 2 to the 32 potential bytes. So page tables somewhere have how many entries there are in it. We have 1 page table per process, and we're going to switch back and forth between those. And all we need to switch is the register value. So to convert to physical address, we take a logical address, we take the upper bits, that gives us a page number. Okay. Now there's a part of this that doesn't fit yet with the x86, right? This is not x86 because we have a single linear page table. a single level page table. We'll get to multi-level page tables in just a second. So if the page number is out of range, which it could be if it is the page table is not big enough, then we generate an exception. If we look in the page table and there's no entry there, if it's not present, we generate an exception. I'll put another check in here. If the permissions don't match, we generate an exception or fault. Okay? And the permissions are, the processor knows whether we're trying to read or write, right? Or the MMU knows whether they're trying to read or write. And so we'll look and see if this is a read or write. And if they support it, execute. The x86 doesn't. So the offset is the lower bits, right? The logical address has the page number here and the offset here. We use the page number to look in the page table. We grab the offset. And now the replace, so just slide in, taking out the upper bits of the logical address and slide in the upper bits of the physical address, where the upper bits of the physical address are whatever that frame number is. Right on.
So where are we putting all of these page tables in physical memory?
So there's two answers to that. One, in physical memory. And, yeah, I mean, just wherever we can allocate them.
So that, and then we just like have to make sure that the page allocator, like make sure not to allocate pages that are going there?
Like anything else, if you've allocated memory, don't reallocate it if you're still using it. One thing to note is we have a page table register. This is a physical address, right? Because if this were a virtual address, one could have infinite regress. So, right. Other questions? We don't get external fragmentation because now all of a sudden all the free memory that we have, we can treat it as if it's contiguous, so to speak. There's potential problems in that the page table itself needs to be contiguous. So if you're starting up a new process, part of what you do to start up a new process is you need to allocate a page table. That memory for the page table has to be contiguous. Did you have a question, Drew?
So that all of this about like seems like the user space. What about the kernel space? Does it have its own page table?
Yes, the kernel space has its own page table too. I mean, it depends on how you set things up with your OS, but JOS and XV6 both have a kernel page table. Yes. And those two are arranged so that the kernel page table and the user page table, the process page tables, are very similar. They both have a big section of address space reserved for the kernel. And if you're the user page table, this stuff is all inaccessible because it's only available in if you're kernel mode. It's transparent, which is really nice. Right? So my compiler linker can just generate position-independent code. Sorry, position-dependent code that loads at a specific location. And then where it goes in physical memory, it'll be all chunked up. You can put individual frames out to disk. We'll talk about that more on Wednesday. But you can actually, if you only had one more page of memory, you could do good things. So I'm going to just take this page that this process is using, that is in part of this process's address space, and just shove it out to disk. And if I ever need it, I'll get it back. Requires an additional memory access. We'll talk about this. This actually is a big problem, and it's why we have another kind of a cache that we'll talk about on Wednesday. Unused pages in a process still require page table entries. We have a workaround for that, which is we're going to use two-level page tables. And we do have internal fragmentation. On average, how much internal fragmentation do we have in the code segment? Or not the code segment, the code area. Half a page, right? The likelihood that we are at a frame boundary, at a page boundary, is 1 over the page size. So assuming it's kind of evenly distributed sizes, on average, we're going to spend about half a page for the stack, half a page for the heap and so on.
Does that assume that each segment's exactly one page?
No, so if I have, let's say, code that is 62.5K bytes, then this is going to take how many 4K pages?
A little over 15.
Yeah, so it'll take 16 4K pages with 1.5K waste, right? Internal fragmentation. So it doesn't assume that our code size is just one page. It can be many pages, but the very end of the code is going to be in a page that may not be full.
Oh, so the last page.
The last page in that segment, yep.
Most pages will be full.
Yeah,
Okay.
yeah. All 15 of the pages are going to be full, and the last one, on average, will be half full.
So it's per segment.
Yeah, per segment here. And I put segment in quotes because we're not saying segmentation. We're just saying different kind of thing that you're allocating that has to be on separate pages.
Sorry, misunderstood.
Okay. All right. Virtual and physical addresses need not be the same size. So they can be the same size as they are in x86, but you can imagine virtual addresses smaller than physical addresses. So question number one, if we have virtual addresses smaller than physical addresses, are the offsets the same number of bits in the virtual and physical address, Dave?
For the second one, for virtual address.
The second one, yeah. Tell me about this size versus this size. Yeah, they agreed, need to be the same size because we're saying this is the offset within the page and this is the offset within the frame, and pages and frames are the same size. So what is different is the number of pages here. So it's really sort of like this. Here's our process address space. And here's our physical memory address space. Is this process able to use all the memory? No, not able to use all the memory. But maybe it doesn't need all the memory. What could we do with the rest of the memory? Use it for other processes, right? So an example here might be if we're running a 32-bit app on a machine with 64 gig of memory, right? So our address space for physical memory is bigger than 32 bits, but our process is only 32 bits. That's all it can access, and that's fine. And it's actually, it likes it this way, because if it had to recompile as a 64-bit process, all its pointers would need to be twice as big, right? And that takes up space and it doesn't need it. So. Or it could be the other way around, virtual address space bigger than the physical address space. So our process looks like this, and our physical memory looks like this.
Would that ever, is that even possible?
Yes. There are a couple ways that this can happen. One way it can happen is very simple. We've got this giant address space, and we're putting the stack at one end and kind of the heap at the other end, and we're just not using that much of it.
Yeah.
So in that case, all this stuff can fit in memory. In fact, let's say this is our app, and this is our page table. Well, all we really need are 3, 4, 5, 6 pages of memory. We don't need any more, even though this is huge. So we could run on a 24K machine or something. Okay. First computer I bought, by the way, 2K of memory. So it turns out there's a lot you can't do with that. All right, holes in the address space. So in your virtual address space, if you have holes, like we just talked about, we're wasting page table. Okay, so if we have 32-bit virtual address space, 4K pages, that's 2 to the 20th page table entries per process. 2 to the 20th at, let's say, 4 bytes per page table entry equals 2 to the 22 bytes of page table. And 2 to the 22 equals 4 meg. So that, it's not too much these days, but it could be a lot, right? So that's 4 meg out of 4 gig, so about 0.1%, something like that. And so one solution is a multi-level page table. That's the x86. I'll talk about this and then I'll let you guys go. So basically what happens is, right, this is our process address space. This is the first level page table. This is the second level page table. On the x86, what do they actually call this instead of page table, Nandika? The first level one. Yeah, they call this the page directory. It's really just the first level. So we break it apart into multiple page numbers. So what we've got in our address is we have our offset, and we have our PT1 and PT2. It's handy if these are the same sizes. They are the same size on x86. So here, we've got that same, this is a very simplified, right? So what we've got is an address space in our process of 6 pages. 3 of them are unused. In the first level, the single level page table, we'd have to have 6 entries. Here, what we can do is, 1, 2, 3. Well, so our first level is going to then itself point to a second level. In this case, it's very simple. It only has 2 entries. This one points to something that could have 2 entries. This points to something that has 2 entries. This points to something that could have 2 entries. We don't have anything here, so we just keep that empty. We don't have anything here, so we keep that empty. This one is full, referring to 3 and 1 for the A and B. This one, right, so this is 0 and 1, 2 and 3, 4 and 5. So 4 and 5, this second level page table is responsible for these pages. It just puts the first one as invalid, the second one here. So if you have a large process with, heap here and stack here and nothing here, you have a first level page table that has entries to second level page tables at the top and the bottom, but here they're just going to be empty. Okay? But remember, each one of these is no longer 4K, because this is a top level page table. So it's responsible for 4 megabytes, I think. I'd have to look at the math on that. But I think that's right. So each of these is a 4 megabyte chunk that you're skipping from doing that. So we use less memory this way if we have a non-full address space. All right, we will continue on with this on Wednesday.